Hello, everyone. We're about to get started. Welcome again to Modular Headquarters, and thank you so much for joining us for our very first Modular Community Meetup. We are so excited to see all of you here in person with us tonight, and a special shout out to everyone tuning in virtually from LinkedIn and YouTube. So before we get started, here's what we've got planned for you tonight. We'll kick it off with a talk from Chris Lattner, our co-founder and CEO, who will share how Max and Mojo are reshaping GPU development and our mission to democratize AI compute. Next, we'll hand it off to Jack Clayton, Mojo Standard Library Engineer, for an awesome live demo of GPU programming in Mojo. We'll have time for a couple questions after each segment, so start thinking about what you might want to ask. And then at the end, we'll open the floor, and if you're hiring, we'll give you the chance to grab the mic and let us know what you're hiring for, where you're hiring, so that folks can come and find you during the networking portion of tonight's event. So afterwards, we'll shift gears into networking, mingling, and just hanging out until around 9 p.m. or so. So without further ado, please help me give a very warm welcome to the legendary Chris Lattner.
Awesome. Thank you, Carolyn. Welcome, everyone. Super excited to see you all. This is an amazing turnout. I'm really glad that you've joined us here, but also on the live stream. We have never done this before, so prepare yourself. This could be a catastrophic fail, but even if it is, hopefully it's fun. So we'll see how it goes. And if it goes well, then maybe we'll do it again. So we'll see how this is. So today, as Carolyn said, I'm going to be talking about kind of two things. One is this whole compute thing. Right, so I've been writing this blog post series. This takes a lot of my time. Is anybody reading this? Has anybody heard this? All right, that's awesome. Sometimes you're like shouting into the void, and so you don't actually know. So I'll talk a little bit about this and kind of do a condensed form, but then I'll also share what Modular is doing about it, which the blog post series has not talked about conveniently. It's building up to it. We'll get there, but it's not gotten to talking about it. And then we'll also talk about some things we've not shared with the world yet that are pretty exciting, how we're opening things up. So with that, I'll just jump in. And also warning, I've never given this talk before, and so be nice. So what are we here to do? Well, we want to rebuild AI's GPU software, right? AI is super important to me. I've been working on this thing for years. AI is so important to the world, but all the software is so bad. And so one of the things that the blog series tries to do is tries to dissect this, understand why it is that something so important with so much money, so much talent, so many people and energy and change and thrash and all this stuff is still, the software is so problematic. And so we've seen, what we as an industry have seen, is that with all the different use cases, with ChatGPT, with all this different, there's a huge amount of demand, right? The applications are endless. The innovations are endless. But on the other hand, and what we've got as a consequence of that is that all the people building software want to solve this problem. There's so much excitement, so many new ideas, so many ways to build a chip. So many chips you can build because it turns out, yeah, data center is a big deal. So are cell phones, so are embedded IoT. So it's like all the different use cases that you might want to use AI in. And this is technology that can touch everything. And of course, while we say AI like a million times in this talk, it's actually about heterogeneous compute. Right? And AI, to me, is also just an excuse to tackle this long-standing problem of heterogeneous compute, CPUs and GPUs, ASICs, like this entire realm of accelerated compute. And so what we're doing is we really want to crack this open because there hasn't been software to do this. Now, there's a flip side of this. So there is a winner in this category. And so it's amazing their contribution, right? I mean, AlexNet happened on CUDA, for example, right? It's amazing that this has happened, but we are kind of at this inflection point. We're kind of stuck a little bit as an industry. And so tonight, we're going to dig into this. And so I'll briefly talk about what is CUDA and why hasn't anything worked, but the more exciting and interesting part is talking about, hey, okay, modular people, like, you've been working on this thing for years, like, what does it mean? And so we'll talk about that. So first thing I wanted to say is that CUDA is an amazing thing. I have a ton of respect. And again, I think we as an industry have a lot of, we need to give CUDA a lot of its deserved respect for catalyzing AI, right? It made TensorFlow and PyTorch possible. Like a lot of these things happened really because of CUDA. AlexNet, again, like that it catalyzed the deep learning revolution. Tons of stuff has been built on top of CUDA. But there's the flip side, right? Which is CUDA is actually not that great, right? CUDA made sense 18, 16 years ago, whatever it was. But the world's moved on. CUDA hasn't, right? And so what CUDA has done is it's piled up more and more and more stuff to scale into new use cases. But now it's this rickety moat. It's a moat, but it's also a swamp that is surrounding it. And you can feel this. You can feel this in the systems we have today. So the systems we have, not to pick on any one, but they're this cobbled together pile of different technologies come together over the course of many years. And many really smart people have worked on these systems. Like this is not negative about any individual engineer or person or product manager or whatever, but everybody's always looked at their part of the problem. And so how do we take, given all the stuff that exists, how do I have impact by making my thing better, given that everything else is somewhat unfortunate, but it's convenient? And so as you do this, as you iterate, as AI changes, as hardware changes, as all these things keep going, you get complexity. Complexity is the enemy. Okay, so what else is wrong with CUDA? Okay, obviously it runs on one vendor's hardware. The other thing that's funny about CUDA is that it only runs on GPUs. Even NVIDIA's building CPUs. They have this whole Grace thing. They're very proud of it. CUDA doesn't run on that. Super interesting. The complexity, the closedness, the proprietariness, and innovation in and around the broader ecosystem. And so we're also blocked because if we want things to move fast, we need that vendor to go do this. All due respect to CUDA, it is not very Pythonic. I find it very exciting, very flattering that NVIDIA is now adding tons of Python-y things, and they're trying to like fit all the stuff that is Python with NVIDIA-specific stuff, but core CUDA is not, and a lot of the ecosystems are not using the technologies they're introducing. And so if you want to have state-of-the-art, best TCO, best power of the hardware, you have to use CUDA C++. C++ is not very AI-centric and not very Python. C++ is, I think I'm entitled to say this, C++ sucks. Are not awesome. Compile times are miserable. If you don't understand that, just ask me offline. I can explain this. And this whole stack just requires deep, intricate knowledge of like all these things which are poorly documented. And so what does this mean if you're actually building systems? Well, it means that like cuDNN, for example, is a massive library ecosystem. You put all this stuff together, all of which is kind of cobbled together, and you get these big containers, and the containers vary, but 15 gigs is not unusual. Sometimes you can get 50 gigs, like, this packaging and dependency system just becomes a mess. So it's not just me that sees these problems. Like we just picked a random collection of the pain that people are suffering out there. Just getting CUDA versions to line up with PyTorch, nightmare. If you want to do something on AMD, well, you don't have CUDA, and so you have another nightmare, or a different set of problems. If you want to have, any of these things going, on the one hand, the demo looks really appealing. You can follow the little tutorial, and you stay on the happy path, you get to success. But then you try something slightly off the path, everything breaks. The magic is gone, and now you have to go debug everything in the software stack and try to figure out what assumption at what layer didn't compose on something else, and so now you're stuck because the beautiful demo didn't scale. And so this is AI development today. So there are different theories on how to fix this. So one approach, which lots of people take, for example, NIMS, say, okay, well, all the software, all this ecosystem is such a nightmare, nobody can get it to work. But there are very specific use cases. If you want Llama 3, we can go tackle all this complexity, get Llama 3 in this one config to be super optimal and perfect, put in a fake box. And that works. But the problem with that is you've destroyed a lot of the value of AI. A lot of the value of AI is it's not about one thing. A wide variety of use cases. You might care about latency, not just throughput. You might care about a slightly different model. You might want to put in a LoRa adapter or something. And so a lot of what the power and the magic of AI is about the innovation, the research, the velocity in which people can move. And so I find this like make everything fixed function solution to be fairly dystopian. Like it destroys a lot of what I believe in terms of innovation and the velocity and the progress in the real meaning of what has made AI successful. And so given all these problems, why hasn't anything worked? Well, the blog post series kind of goes into this. First, you have to understand why it succeeded. And so this is something that, again, different people look at different technologies in different ways. What I try to do is I try to understand and look into it and understand, okay, well, it's not an accident that things become successful. Let's go understand what happened. Well, CUDA succeeded for a number of reasons, including luck, but not just luck. They built an amazing gaming ecosystem. They built on their install base. They had PCs with laptop GPUs and things like this. So it enabled people to learn how to program CUDA on inexpensive devices and then scale. That's actually a really big deal. And that's something that, for example, if you're building just a data center line, you lose out on. Of course, they invested early, even when it was like almost fiscally irresponsible to do so. Like NVIDIA, the GeForce 3, I'm super impressed. It was like a huge bet for the company on programmability. And so they made really big bets when it was obvious, which I have tons of respect for. But then what they did is they said, okay, well, as AI is evolving, as TensorFlow and PyTorch are evolving, in apparently good interest, go make it go fast on our hardware. The consequence of that is that then they also said, okay, well, all of these frameworks were now co-designed and locked to their hardware because it's locked to CUDA, and therefore it's very difficult for anything else to come in. And so PyTorch and TensorFlow both have they accidentally knighted CUDA. So DeepSeek was a big deal. And so that was the for starting the blog post series, because I think to me, DeepSeek it's just another day in the neighborhood of AI, right? It's like, okay, well, you wake up and now things go 10x faster than they used to because new research, right? But I think DeepSeek was more than that for the world. DeepSeek, both the geopolitical ramifications, but also the technological ramifications, caused a huge wake-up call. And I think a lot of people were talking about compute in a really new way. And so one of the things that's super interesting to me is that they got a lot of attention by, air quotes, going down to PTX. This is something that if you're a GPU programmer, you kind of have to routinely do, because tensor cores are you to do this, right? And I think the world didn't realize just how problematic the CUDA ecosystem is, and the fact that it's not just DeepSeek that does this. Like, lots of people have to do this, and this is a bug, not a feature. What I believe to be true, and others as well, is that efficiency gains, like what DeepSeek brought, lead to increased consumption, more use cases, more demand. AI goes to more places because as the cost curve changes, as you make things less expensive, suddenly you can do that technology. Satya pointed out Jivan's paradox, which is a very interesting way to look at this. Now, but the problem is that, okay, well, if you go look at DeepSeek, and I'm super impressed with their work. They've been opening a lot. They've been publishing a lot. I mean, they've massive contribution to the AI ecosystem. They are so advanced. they, as well as some of the top research labs, are doing things at such an advanced and incredible level. But you have to be at that incredible level where you can afford to pay hundreds of researchers and do this kind of work to be able to unlock the power of the silicon. And to me, like, on the one hand, it's amazing what can be done, but it's also, again, kind of dystopian if only the top 5 research groups in the industry can afford to do it. I don't think that's a path to success for us as an industry. And so this is where democratizing has many different meanings, but let's get more people able to participate in this. Now, there's lots of attempts to solve this problem. I'm going to go through this lightning speed. OpenCL is the one that should have won, right? It was the industry standard. It's a great technology. I worked on it when I was much earlier in my career. But the problem is it turned into a committee project, right? And it moved with committee. It didn't support tensor cores, had a lot of problems that prevented it from actually scaling into the AI ecosystem. And what, in contrast, you look at CUDA had a strong leader that said, look, you know what? I'm going to solve the most important use cases in their opinion, and they could drive it much stronger in a specific direction, which you may or may not agree with, but it showed a lot of velocity. And I think this is the problem that I see with a lot of community or standards bodies type approaches. What about I'm a fan of compilers. Does anybody else like compilers here? So compilers are good. So TVM is, I think, fading away now. XLA is something that I have to work on, so I know a lot more about it. AI compilers are because you get generalization. Kernels don't generalize. In AI, you have many different kernels fuse them. And if you have to write all permutations of all fused kernels, you quickly run out of kernel engineers who can do the work to actually tune it both for all permutations of kernels, but then all generations of hardware, and then all the D types, and then all the all the different use cases, and suddenly you run out of kernel engineers. You just can't scale. And so AI compilers are awesome. Go compiler people. And it solved this by making it so that you could synthesize in an automated way a novel kernel by using compiler techniques. Now, the problem with this is twofold. One of which is that many of the projects never could deliver the peak performance of a kernel author. And so a lot of them ended up using like the CUDA libraries for matrix multiplication, for example, and just did kernel fusion for the easy cases. One problem. But there's a much bigger problem. So the much bigger problem, and compiler folk, I love you. We make fun of the kernel folk because they don't scale, but it turns out compiler folk don't scale either. So if you say you need a compiler engineer in the loop to be able to innovate in algorithms, then you quickly run out of compiler engineers, or you run into this problem where you may have an amazingly smart compiler engineer, but the compiler engineer doesn't know the cross product of the compiler algorithms, the hardware, the D types, the crazy new research paper that just got published, the hack that the hardware has that allows you to cut 3 cycles out of the inner loop of the thingy, and all of that into one brain. To me, what I learned from XLA is it doesn't scale. And there are like, when I was there was like 2 or 3 humans that could do some of this work. And it was just a huge bottleneck for TPUs, and it was a huge problem. Now, these technologies also have a different problem. That problem is called Gen AI. And so a lot of these technologies were designed for traditional AI, and they made sense in that context. But when Gen AI came over, it really changed the. It wasn't about putting a ReLU onto a matrix multiplication anymore. It was about flash attention, right? And so when these things happen, when you get MLA, you get like these much more advanced algorithms, suddenly the world got so much more complicated that the compiler approaches, or this category of compiler approaches, just didn't scale. And so again, we found ourselves as an industry writing all the kernels. And when you're writing all the kernels, typically those kernels got written in CUDA, because that's where all the installed hardware was. And then again, everything got locked onto one vendor's platform. What about Triton? So I'm a big fan of Triton. People like Triton. Triton's a good thing too. Triton is one of these things that said, okay, well, CUDA C++, not that great. It's really hard to use. It's very low level. Triton and Phil and other folks did a really good job of up-leveling the programming paradigm and saying, let's get the world into Python. Let's get people off of individual threads and start thinking about a much higher level tile-based programming model. And I think this is a huge step forward, and this has been very popular and very successful in the industry. This really held when PyTorch 2 came out with this inductor and dynamo and this technology stack that really kind of endorsed Triton and the solution to PyTorch. Now, there's some problems with it, though. So first of all, it's a fancy compiler. Compilers are not perfect, and so you get a lot of productivity, but you also give up, it varies, but somewhere on the order of 20% of performance of your chip. 20% of cost on a GPU is a lot. And so all of your experience, what I've been told by many folks, is that Triton isn't really used for state-of-the-art Gen AI inference. Like, it's been very popular for training and things like this, where time to market and velocity and things like this and research are really important. But I've heard of many labs that use Triton for research and prototyping and things like this, but then have to rewrite in CUDA C++. And so that's value, that's contribution, that's awesome that they're making a use case better, but it's really deeply unfortunate when you have like, okay, I prototype in Visual Basic and I have to rewrite in C++ or something, right? And technologies. I think Triton also has another hidden secret, which I don't know if everybody in this room will agree with me. I'm sure some of you work on ASICs. Triton was not designed for ASICs. And so the programming model, the way the memory and the pointer model work, like all this stuff is very GPU specific. And so while it's appealing to think, okay, well, I can just write this code, the inner secret of Triton is that you don't even get portability across NVIDIA generations. Like, you definitely don't get portability off. And then you end up in this realm where, okay, well, you can't express the full power of the hardware for your ASIC. Well, suddenly, if you're building a chip, it's really quite problematic, because giving up more than 20% performance means your chip's not competitive. And it's hard enough to keep up with NVIDIA on just flops and features and things like this in the hardware. But if you're holding back the hardware's potential based on software like this, it becomes an even bigger challenge. So yeah, so what I learned from this is really quite important, which is this is incredible validation that CUDA C++ is too hard, and I think the world wants something that's much easier to use. And so I think this taught me a tremendous amount. But the flip side of it is we can't give up what makes CUDA great, and that's performance. What about MLIR? Well, I'm also a fan of MLIR. Does anybody else like MLIR here? Is this a good thing? So the blog post talks about this because people always ask me, in particular, like, why didn't MLIR solve this? Like, isn't it supposed to be the thing that solves all this stuff? And this is where I get very sad because it's also very personal. And so MLIR is amazing. I'm very excited to see how wide it's gone, and like so many people use it for so many things. It is widely successful across enabling a tremendous number of chips. I know some of them, which is amazing. I don't know all of them. But the problem is it doesn't provide an end-to-end AI stack. And there are things out in the ecosystem, there's Erie and many of these things that have come up and existed, but they haven't really solved this problem. And what happened is a lot of the MLIR ecosystem tried to build a better XLA. This is probably the easiest way to explain it. But XLA got left in the dust by Gen AI. And so a lot of the technologies, a lot of the dialects, a lot of stuff in the MLIR ecosystem is really cool, but it's really it's like a Tinker Toy set. It's like some assembly required. And so I think MLIR is an amazing thing. It's a great, obviously very proud of many of the people that have helped make it possible, but it's not solving the CUDA problem. It's enabling people to build systems in this space. Okay, what about hardware companies? Again, hardware makers are awesome. The challenge with innovating in hardware is that the software teams just don't have a chance. It's just so hard to do this work. And everything ends up being stacked against you. Not only is NVIDIA seeding all of the software ecosystem and making it CUDA specific, but Gen AI is changing so rapidly. All the technology is moving so fast. There isn't a thing really to build into. It depends on the company, but hardware leadership often doesn't understand how hard it is to build software, because the hardware leadership, again, I don't know, I don't speak for every company, but many senior hardware leaders were brought up, say 10 years ago or 15 years ago, and typically they're building a CPU or they're building a networking thing, building some other ecosystem. And if you're building a CPU, enabling software means build a GCC or an LLVM backend. And then I get Linux, I get web browsers, I get like email, I get everything with a constrained investment in plugging into a thing. Yeah, it doesn't work that way. There is, and this is a challenge for everybody. And so as a consequence, everybody ends up signing up for this problem that seems like it's easy, you get a thing to work, but then when you get to the general case, suddenly it gets exponentially more difficult. I talked to a lot of folks who are going in the secret. So what if, this is a long way of saying this is what the world's been dealing with. And when we started Modular, we knew a lot of this. A lot of the details were different, but a lot of the lessons learned, I had experience with TPUs and many other things. And so what if we could build this? What if we could really crack this? What if we could change the trajectory? What if we could do something that could be a fundamental contribution and help solve some of these long-standing problems? I think this would be pretty cool, be a good thing, but it's also really hard, right? We can't expect to just do the same thing that didn't work before and have it work this time. We have to do something that's quite different. We have to redefine the rules. And so this is what, again, the crazy folks at Modular have been doing for years, is building many of the different pieces. And we've been going through years of research, because it's pure research required, to be able to build new abstractions, new concepts, new technologies, new syntax, new things that all can come together that we think can actually help with this. Now, we're still very early, right? This is not a small problem. This is a big problem. I have not solved this today, but I am really, really excited that just this quarter, the amount of progress we've made, just next quarter, what I know is going to happen, and through the rest of this year, it's all coming together. And so I'm really happy to talk about what this is, what our approach is, and share this with you. And obviously, if you're interested, we'd love to talk about it. And so what is Modular building? Well, we want to build a new world without CUDA. And so I love NVIDIA. They're an amazing company. Their hardware is amazing. The challenge I see is with CUDA, and what I want to see is something that can run really well on NVIDIA and run on other places, because that hardware is very important to the world. And so it's not really NVIDIA's fault. It's just what CUDA has done to us. And so we want to go build something that can help scale into this. How do we do this? Well, this is a big problem. This is an industry scale problem. And so what we did was we broke this down into pieces. And so first, there's a language aspect. So you run squarely into this problem of domain-specific languages are difficult to use. They have bad tooling, debugging, all the stuff that the Triton blog post thing talked about. But then on the other hand, you have all the existing languages like, Rust and Swift and C++ and stuff like this. They're not really designed for heterogeneous compute. Some of them can be used in some ways, but they're not designed for it. And so one of the core assumptions that we made is AI is important and will gain in importance, and hardware is going to get more weird, and we need to be able to scale into all of the things. And so that squarely, I tried to resist this, but I squarely ran us into the language problem. And then ... I think what many of you know is Mojo. Mojo comes out. Well, so Mojo is a really cool thing. You'll see some demos later. I'm very excited about the pace in the progress that Mojo has made. But what it enables you to do is actually be able to get the full power of the hardware, have a development experience, be able to scale and run on wide ranges of different devices. And it's designed for this heterogeneous, talk to weird tensor cores and all the goofy things that hardware people keep coming up with, because that's inherent to the problem. And so Mojo is not a solution, but it's a really important part of the solution. And when we talk about higher levels in the stack, all of the code that we use that runs on the GPU is written in Mojo. And this is what we mean by not using CUDA. So we don't use cuDNN or vendor libraries or Cutlass or like any of that stuff. We've rebuilt that entire ecosystem. Well, if you take a step out, now you get to, cool, you can write GPU kernels. How do you actually use them, right? And today, I love people to write GPU kernels, and you'll learn more about that later. But a lot of people work at the AI layer, right? They work at, hey, I have matrix multiplications and convolutions, and I have a transformer, I have a dense layer. I want these, I want a module. I want to think about things in terms of AI. And so what we've built is a very tiny beginning. It's not fair to call it an AI framework yet, but it is a very simple inference-focused AI framework in Python that allows you to develop models that are super predictable, super good control, designed for Gen AI, makes it so we can solve these problems and get the full power of the hardware, which I think is really, really, really important. Now, this framework, again, it's very early, and so it's exciting, but it's still coming into its existence, called MAX. It has serving components, it has the kernels, it has a bunch of different things in this ecosystem, but it also gives you an auto-fusing graph compiler, you a lot of the technologies that are quite advanced and that even the existing their systems don't have yet, which dramatically simplifies it. In designing the abstractions, this is why Modular's project for 3 years was so key, designing the abstractions so that you can compose, so that we can get this thing simple at the bottom, enables us to make a scalable interface going up. We're just now bringing in even bigger, higher level pieces, and so we've only just started talking about this, but we have things like, okay, well, once you solve for the code that runs on a GPU, and now you start building pipelines, and you start doing at the max level very fancy KV cache optimizations and like all this kind of stuff. Well, suddenly you get to the problem of, hey, well, I have 200 GPUs or 2,000 GPUs. How do I do them? And so what our technology is, which we're not going to talk much about today, but if you're curious, let's talk about it, is saying, hey, if you're an enterprise and you have a lot of GPUs and you're running a platform team and need reliability, you want your product team to be able to innovate in models and do stuff, and then the platform team shouldn't have to like chase AI research. They should be able to manage the GPUs. And so this is a natural set of concentric circles where everything builds together and builds on top of each other, and it's actually very simple, which is. So let's dig into each of these. I'll give you the whirlwind tour. So Mojo, assume that most of you are familiar with this. I'm not going to talk too much about it because Jack will talk about it later. Well, Mojo, by definition, hopefully you know, is a Pythonic language. So it is not Python, but it is designed to be very familiar to people who are working with this. By the way, Mojo Python Interop is coming really well, and so maybe in a month or something, there will be some really cool announcements about this, and so you can extend existing Python packages in Mojo and make that super easy. But our focus has been on GPUs, right? And this is the core problem we need to solve, which is we need GPUs to go fast. Advanced type system, for example, Mojo has dependent types, full power of the hardware, full access to MLIR, full access to like inline assembly and tensor PTX and like all this stuff. but then it interoperates with the existing world. And so this is, again, the bottom of our stack, but a really, really, really important component of this. Max, I think I already talked about this. This is the framework level. This gives you something that's for a VLLM. You get OpenAI compatible APIs if you're serving, but if you want, you can go down and say, hey, just run a subgraph on a GPU. And so you get a very nice GPU programming experience. This all you can use this in Mojo, but like the preferred API is all Python. The reason we do this is just lots of people are already used to technologies in the space using Python. Mojo is required for getting GPU performance. Python is fine for like I'm building a graph, and so we said, okay, well, let's use Python for what it's good at. By the way, you say build a new framework, that sounds insane, and it is kind of insane, but this is not something where we have like Resonant 50. We're now at the point where we have over 500 models and variants and things like this in our native stack running on a wide variety of hardware, which is pretty cool. And so we'll talk about where you can find these later. Deployment, this is also a pretty important thing. We totally believe in meeting people where they are, and so we make it super easy to get a Docker container, and we'll give you pre-configured ones. They're super small. This is one simple way to understand what without CUDA means. These small containers, by the way, it's kind of an open secret. Please hush, hush, don't tell anybody. The same binary runs on NVIDIA and AMD GPUs today. We haven't announced that. Please don't tell the world yet. That's actually a pretty big deal. And that's a thing nobody's ever done before, right? And so this is very telling the world and telling the story about this, but this will have profound implications. So let's talk about license. So this is something I'll just be straight with you. I don't think we've done a great job at. I'll tell you the thinking, but then I'll also tell you why I'm very happy it's time for new thinking. So the thinking was, we're building a research project. It turns out it took 3 years to go from like that we have an idea that we could build something great to I believe it's working. Like the I believe it's working moment was really this December release that we call 24.6, which is where we could run state-of-the-art performance on A100 with one model, and that required the entire tech stack to line up and work right. And in that moment of 3 years of development, the decision we made, which you can agree or disagree, is we said, look, the risk is, can we achieve our goal? And so we've kind of been wavering between, do we want people to adopt this, not, or is it a distraction, or is it helping us or holding us back? And I'll take full ownership of this. I've made bad decisions, and like we tried to keep the license weird so that it didn't grow too fast. And because if you grow too fast and you get all this people and dependencies, and that's bad if you're changing it. But we want to be open, but super confusing. So we're fixing that. And so we're fixing it for a number of reasons, but the biggest reason is it's the right time to do that. And I'm happy. I mean, obviously there's lots of, I'm never fully happy. I think everything can always be better. But I'm getting happier with the, we're really close. And so actually this is where I'm very happy that we get to actually talk to people and do this, and license and availability piece of it. Also, I've said this before, our plan is to open this stuff over time. So in about a week, maybe 2 weeks, we're about to open source about 250,000 lines of Mojo code, which I think will be pretty interesting. And so this is all the flash attentions and matrix multiplications and all the high performance kernels for at least 3 GPUs, all open Apache license. Very excited. This will be, I think, a big moment, and I'm very, very, very excited. The whole team doing this. I'm so proud of the team, by the way. It's like what they're able to do is just ridiculous. So this will be a big deal. Stay tuned for this. We're still going to open source the Mojo compiler. That's also coming. Not quite there yet. Let's get over this and see if it crushes the team or not. But we're still on track for this. I think 2026 may be conservative, but we'll see about that. And we have a new license. And so the license on Max has been super confusing. And it's super confusing. And before I tell you what we're doing, I'll tell you why it's super confusing. Early when we first came out of stealth and we were starting to talk about what we were doing, this is me taking responsibility. I said, as a technology, we want to be free and take over the world and people to use it. Max is a commercial product, and like that's a different thing. And I drew this line between the two because that's what we were thinking about it 18 months ago or something like this. But what we want is we want everybody to use Mojo and Max. And so we can't do that if it has a weird license. So what we've done is we've defined a new license, which is way better, Max community license, or the modular. And so what it means is you can go and use both Mojo and Max for whatever you want for non-production, non-commercial use. So if you're a researcher, all that stuff is super cool. Oh, by the way, if you're production commercial, you can also use it for anything you want on x86 and NVIDIA, which is the only hardware we support right now. For other things, we'll figure it out. We need to actually do them first, but we may relax over time. We're gonna be a little bit conservative on that. But the only requirement for commercial use is please tell us and let us use your logo. It's like a small thing to ask. Scale it on 10,000 NVIDIA GPUs and do amazing things. That would be awesome. Just like tell us so that we know and so we can tell investors so that we can be paying for it and do stuff. This is a big deal. And so what we're doing, and just so you know, is we're trying to take away any of the reason anybody would want to use CUDA. Right? So CUDA, proprietary closed source kernels, you cannot understand what's happening. If it breaks, you get a weird stack trace. In 2 weeks, the kernels will be open source. You can go look at them, you can change them, you can enhance them, you can tell us that our engineers are not as smart as your engineers or whatever. Let's work together and fix this, and let's make this thing better. If you want to build a scalable LLM service and compete, like, fine, that you can do that. That'd be annoying, but this is the way the world works. But we want to see the technology go far and wide, and we want to see what you can build with it. And so this, I think, is a really big moment for us. And this has always been part of the plan. I don't think we've communicated this well, but this has always been part of the plan. But I'm really, really, really excited we're here. And so this is a very special moment for me. If you're interested in using it commercially and you want to scale, we have a very fancy enterprise edition. And so please let us know if you do have hundreds or thousands of GPUs. If you want commercial support, yeah, you can pay us for commercial support. That's fine. We have other stuff that kind of goes in this category, including the cluster management and other products like that. But we want this, you can call it like the VLLM and down technology to be free for people to be able to go use it and go do really cool stuff. And my core hope, my core belief is that as we unlock this industry, as we break down these barriers, like new research will happen. And I'm really, really, really excited about that. All right, so what does this mean? So there's lots of things. Another thing that's about to drop is pip support. This is another ongoing quest in terms of figuring out packaging and how we distribute our stuff. Pip support, I think this command technically works if you know the right URL. You can bug other people. I don't actually understand how pip works. This is really cool because now it integrates with all your normal developer flows and all this kind of stuff. And so this is also another big deal. If you're interested in models, we have this thing called builds.modular.com. This is where you can find hundreds of models and variants and things like this. The cool thing about this is you can click on each of these things, and then there's like four commands. Run, install the stuff, and get it going. This is the benefit of building a vertical stack, by the way. Again, my enemy, my number one arch nemesis is complexity. And so by getting abstractions right, by building this thing the right way, we can delete a lot of that complexity and make stuff that actually just works. And so this is a lot of the value of what we're doing here. There's also other things, recipes, and other examples you can follow. The recipes are cool because you can say, hey, I want to build show me an example of a RAG solution, or show me how to build an agent using this stuff. And we make it super easy. And the cool thing about this is the stuff plugs together really nicely. And it builds on standards like AI endpoint standard, and you can get going really quickly, which is. So that is all I wanted to ramble about. I hope that's interesting. Teach a little bit about things that are coming soon. We have obviously way, way, way more stuff coming that'll come over the next month. But I'd love for Jack to share.
Yeah, thank you so much, Chris. Before we let Chris go entirely, not getting away yet.
Do I get Diet Coke?
You do get a Diet Coke, but you also get some questions if there are any questions in the audience. Yeah, we'll start over here.
So you mentioned Triton is like over optimized for OpenAI's needs. Do you feel like you've made any assumptions in the development of Mojo that make it over optimized for, I mean, maybe it's over optimized for AI and, I can't run molecular dynamic simulations anymore.
Mojo right now is over optimized for. Let me be very honest with you, sugarcoat it. This is the problem with building language or something as horizontal as Mojo is that, and again, I know this annoys people, but case has been to build AI stuff. It's really hard, and so what has constantly happened is there's several very smart Mojo engineers in the room here. They're working on like, okay, I want to make lists work amazingly awesome and fancy like Python, and then they get really pulled into how to split compilation work again. How do I make compile time go faster? Very fancy meta stuff for tile-based layout. Okay, we need to make the compiler 10x faster. Right? And so as far as I know, there's nothing in the software stack that is AI specific. And so if you want to do biochemistry or oil and gas or something like this, or game of life, like awesome, go nuts. You can totally do that. But the consequence of our approach, which by the way, I think is the right approach for building a technology, always dog food and build something yourself, is also why I wanted it in research mode so that we could iterate rapidly and be very focused. But the consequence of that is that we haven't built out all of the features that we want Mojo to have. And so what you'll see across even this year, allegedly the Mojo team is publishing a roadmap very soon. And what you'll see, they're now finally getting time to invest in broader ecosystem enablement features, for example, Mojo Python interrupt and things like this. So, yeah.
Hi, thanks for Mojo. It's really awesome. I love it so far. When I run it on my Mac, obviously it doesn't have GPU support yet, right? So I was trying to dig into how I could possibly implement that myself. I don't think those tools are available yet. Is that right?
That's correct. So I can't commit to anything, but our hope is that we'll enable that this summer. So, and then can help.
Hi, this is Mahi. We use Mojo because primarily for the language. I mean, we love it. It gives great productivity. We are an end user app. We run on iOS and Android. Any future plans for edge computing or iOS or Android?
This is outside my expert. Well, so I mean, I have some experience with iOS, but the I haven't spent a lot of time on this the last few years. My understanding is it runs fine on iOS and Macs, and people put on Raspberry Pis and stuff like this. But the best place to ask is on the discourse.
Sure.
The forum. Yeah, forum.modular.com.
Thank you.
That'd be the best place to ask. And there may be some weird API thing or something that I don't know offhand.
Hey, Sean here. I've got a question about interop with native code beyond sysFFI. In particular, if you want to reach into Rust ecosystem stuff for like Apache Arrow or a bunch of the great SerDes work that's been done there, and you want to like do a lot of data processing and pull that in. I'm curious like where some of that stuff is going.
So I don't know of any work specifically around Mojo Rust interop. That's super cool. I'd love to explore that. Mojo does have good C interop, like you talked about the FFI module, and so I assume that Rust talks to C and has a CDECL type thing or something. And if that's the case, Mojo can talk to it, and like we can meet in the middle. But I don't know specifically how that works. I also don't know how the ownership systems, getting them to line up optimally, would work. But I would suggest starting with like a glue generator or something. That would be an interesting way to just like synthesize some bindings.
Other questions for Chris?
Jeremy here. I was wondering, I mean, you mentioned a lot about GPUs and things. What about non-GPU accelerators, exotic data flow architectures, these sorts of things? How is that going to play into the Mojo modular ecosystem?
So I love all the chips. And that includes things that are way over my planning horizon, like quantum and analog, and like I'm just such a nerd, right? FPGAs, like there's so many things out there. The way to think about Mojo is it's useful for anything that has a program counter. And so it's not going to help you with an FPGA, because I mean, you could do high-level synthesis type stuff theoretically. I'm not a fan of that, and if you want, I can talk about it over beer. So you could theoretically do that, but it's really good for something with a program counter. And so if you have a weird ASIC, you have something that has like a gigantic systolic array, or you have a RISC-V core that's controlling a video encoder, like it's very useful for that kind of stuff. We haven't opened up the ability to add new backends yet. That's something we're interested in doing, but it's not like in the next 3 months time horizon. So.
You mentioned DeepSeek. I've only found one article that basically sort of said they decoded the binaries and found out, there's just a bunch of special opcodes that NVIDIA sort of quasi documents in the documentation. So you have to sort of give the question is that the Chinese programmers obviously had some serious brains to take PDX and say, this stuff is crap. We're going to generate the real lower level machine code. So my question is, does anybody decode all of the kernel binaries to find out what the translation that NVIDIA did it was sort of less than optimal? Because effectively what you're doing is you're saying these guys are smarter than we were, and they've sort of done a better transformation with the PDX into the raw hardware. So we ought to be able to, NVIDIA ought to be able to figure that out themselves and say, hey, they set the bar that we're missing,
Yeah, so the lesson I take from DeepSeek is slightly different than what you're saying. I think what I hear you say is that you're saying the DeepSeek programmers figured out how to use NVIDIA's hardware better than NVIDIA did, right? But I don't think that's actually what happened. What actually happened is they invented new algorithms that NVIDIA hadn't hard-coded into CUDA yet, right? And so because they invented new algorithms, they had to go to the same primitives that NVIDIA and many other Cutlass programmers and other things like this had to use. And so the problem with the CUDA thing is that, again, the NVIDIA approach is saying, like, find the important use case and then hard-code it into the libraries. And so that only works if you're chasing research. That's not helping if you're doing research. And so this is where, if you go, again, just a week or so, you can go pour over more Mojo code than you ever wanted to know. By the way, please train your LLMs on it. You can go look, and we go directly to PTX also, because you have to get the highest performance. And so it's not, I don't think that was the novel thing. It was more about
saying, here's what NVIDIA did, and here's what we did by tweaking, stuff in all the documentation of NVIDIA and saying, oh, there's these special opcodes that won't push over slow catch. So there's somebody says that they were also did a combination of certain algorithms, but also they had a little range applying to the generated machine code too. So
yeah, well,
where's that trade-off? Is it all algorithm or is it some of the other machine code?
Yeah, so you're beyond my knowledge. So I'm a nerd in many things. I don't know the full details of what the DeepSeek team did. But again, there's no magic. My fundamental philosophy is there's no magic, right? And so there is an optimal set of instructions that will make any individual chip go fast. And so, you can write theoretically everything in assembly, and if you care about exactly one point solution, you can do that. But that's not what AI is. What AI is an ever-evolving set of use cases. There's an evolving set of algorithms. There's like research innovations happening. Like every day there's a new paper. And so I think the challenge, to me, the way I define success is making it so you can get the full power of what, for example, a DeepSeek engineer did, but that you can then get the software engineering benefit and the scalability and the leverage of compilers and of abstraction and of software engineering, so that you're not having to literally write everything in assembly language. If you go back to me making fun of compiler engineers for making fun of kernel engineers, like my whole philosophy and the philosophy with Mojo is to say, look, kernel engineers are amazing. They should be empowered with compiler algorithms. And so what Mojo does is it says, let's take much of the algorithmic smarts and put it back in the kernels, and then allow the kernel engineers to have superpowers, so they get the power of generalization, they get power of metaprogramming, they get the power of what compilers will get at, and it's in, air quote, user space. It's in the Mojo source code, instead of being hacked and hard-coded into the compiler. And so I love compilers, I love compiler engineers, obviously, right? But the way to factor this world is to make it so that you have more people that can participate in the space and make it so that their work can scale. And I think that's fundamentally the contribution of what we're building.
did you have
Can you elaborate on the self-hosted K8s in your commercial license?
Self-hosted which?
You had a clause about self-hosted K8s. I'm assuming Kubernetes.
Yeah, so I mean, our general approach is that you can use for free the kind of VLM or TRTLM subset of the stack, and so you can deploy it yourself on your own Kubernetes thing and scale and do whatever. We can make that much easier for you if you want to use our management layer and our cluster solution. Yep.
I have a question about the abstraction levels. So in your slides, you mentioned OpenAI Triton library. In that case, you were saying it's not as fast as CUDA, but Triton is actually, I'm sure you know maybe better than me, but sort of at least the Triton I wrote is quite low level, much more low level. It's actually more low level than CUDA in a way. And first of all, I was surprised there's a gap. So this is something I need to learn more. But second, and excuse me if you explained that, but
sure.
Do you think Mojo is higher level abstraction level or lower than an OpenAI Triton?
Yeah.
And
great.
if it's higher, how could it be faster?
Great question. So this is the secret. Okay. So I'll try to explain this in a slightly different way. Again, I will write more blog posts, time permitting, but I did not. I mean, it's strange, an epic book at this point. But so the problem with Triton, the problem with the Triton approach, because it's not just Triton. There's many of these systems, and there's DSLs. There's like tons of them. But the problem is they're saying, let me give you a programming model. So the tile-based programming model that Triton has. Let me provide a very fancy compiler that does loop pipelining or whatever set of transformations that it does. And then let me expose that to you as a programmer to make a common case simpler. And so Triton's really nice for writing attention blocks. The vast majority of what Triton gets used for is writing attention blocks. But there's a problem because the compiler goes and does stuff, and sometimes it does the right stuff, sometimes it doesn't. Sometimes performance is good, sometimes it's not. Maybe you're an expert. I don't know. The 20% number came from Phil Tilley, who's the author of Triton, and so I was not trying to make an innovative claim. I was just trying to repeat what he has said publicly. But Mojo has a fundamentally different approach. And so Mojo, the language, is lower level. And so you can write threadindex.x, you can write all the way down to, if you're building an ASIC, you can write assembly, go into the whatever your tensor core is, or like you get full power of the hardware. So it's a low level language, but then it has a very powerful metaprogramming system. And so the metaprogramming system allows you to build, for example, tile-based algorithms in Mojo code. And so it's not hard coded into the compiler. And so the thing that we open source, not only does it include all the kernels, but it has all of our abstractions for building kernels. And so we have a thing called layout tensor. Layout tensor is roughly the API used to talk to tensor cores. And it talks to multiple tensor cores that have different layouts, and it has an index algebra, and it has a whole very fancy set of abstractions that are all built in Mojo. So they're libraries, which means that if you want to, you can totally use those abstractions. They're very nice. I think they should be better, but we'd love help. But they're getting there. They're not done. They're not perfect. But they're getting close enough for us to publish. But if you don't like them, ignore them, throw them away. It's a library. And so this means that you can write, a ray tracer. You could write bioinformatics. You can write whatever, not just transformer blocks. You can write anything you want, and you have the full power of a GPU. But if you like the abstractions for tile-based programming, you can totally use them, and you get high expressivity and a lot of power and portability at coarser grain and things like this. And that's the secret, right? This is about taking it out of the compiler. Tiles are not in our compiler at all. Putting it in the library.
It's not a new question, just a quick follow-up. So
yeah.
You can cross-compile.
Yes. Again.
It's not obvious. Usually, you need to for survey, you need to actually get P5, which is the H100 machine, and compile it. So it's actually kind of cool. Just the only thing you can compile, say, on a normal non-GPU machine, then run this alone is actually.
Well, seriously, have you ever heard of one binary that runs on both an H100 and A100 and an MI300? What I love right now is that I see virtual brains splatter against the wall because your head just exploded. And so, but again, this is, and by the way, all try it yourself. So this is like great claims can be justified with actual proof, but for example, all of our kernels are JITted. Because they're all JITted, this means that yes, you get cross compilation. And the way Mojo works, it was designed, again, this is the mad science that it took to build this stuff. What's that? No, warm up is fast. I think, again, it depends on the model, but if you build like a Llama 8B model, which is, I don't know, 1,000 plus ops in the graph, something like this, and you're JITting it, it JITs and fuses down to 80 odd CUDA launches or kernel launches, something like this. The whole thing end-to-end JITting takes about a minute. DecodeGen makes hundreds of thousands of PTX, completely novel kernels. Like, seriously, built an entirely new language. The whole thing is paralyzed. Like, worked around all the problems with the LLVM. This is not easy. It took a lot of work from a lot of very smart people. So, but I love the brains. The brains splattered that's what we're going for. So.
Take 2 more questions, and then we're going to let Chris enjoy the rest of his Diet Coke. All right, I'm going to try to pass this back here.
You mentioned dependent types. Did that grow out of something specific? Is that just helping to keep the metaprogramming sort of structured somehow? What's going on there?
Yeah, so dependent types, for those that don't know, is that it allows you to build type computation in the type domain, basically. So Mojo has a very powerful metaprogramming system. It's not completely novel. It's directly inspired by Zig. And so Zig has, they call it comp time. And so it allows you to use arbitrary runtime code or nearly arbitrary runtime code at compile time. And it unifies the language and the meta language. And so Mojo does literally that. It unifies the language and the meta language, making the whole thing simpler, make it way faster, et cetera, et cetera, et cetera. The consequence is now you can use arbitrary, what we call parameters in type domain. And so it may blow your mind, but go look at the Nightlies. Integer literals, for example, do like all of their work in type algebra. And so they can be infinite precision, those infinite precision literals that even for floating point, which is really cool. Again, very mad science stuff that most people don't know anything about, which is fine. But that then gets materialized into different integer widths and SIMD types and stuff like this, and it's all made possible by this kind of stuff. And so again, like this is stuff that innovation in PL is programming languages is not something that lots of people talk about, but it's actually it's not about syntax. It's about being able to express powerful libraries, and this to me is the key thing. So, and not having to wait for C++ templates to compile. Both. It takes an hour to compile just the flash attention repositories. It's
hey, Chris. Thanks for the talk and answering all our questions. So I work at a hardware vendor, and we're RISC-V CPUs, so we're not ARM or Intel. And then we have our own accelerators, so we're not AMD or NVIDIA.
Yep.
So when is like a good time for us to meet with you guys to build our own backend, for Mojo? Because I was at the talk I think a year ago now in San Francisco, and obviously that was way too early. GPU was so early then. But I'd love to get this in our hands internally because I feel like it would accelerate a lot of our kernel engineers and a lot of the work we do.
Yeah, amazing. So the answer is probably this fall is my best guess. So I'll share my problem with you, which is we really want to get this. It's like I was talking about earlier. We really want to get this in everybody's hands, but we also want to do things in the right steps. And so I'm really worried about open sourcing kernels. By the way, I'll share my anxiety. We have a small team. I think that the stuff we're doing is really interesting. I don't want them to get completely annihilated. What we're doing is we're putting the. I think can't guarantee that we'll have the right answer there, but it feels ballpark to where we could do some interesting things together potentially. So.
Thank you so much.
How about this? Definitely not until fall. So, so maybe fall, but definitely not until then.
All right, let's give another round of applause for Chris. So if you have any other burning questions for Chris, he will be around during the networking portion of tonight's event, or you can always feel free to drop your questions in our community forum at forum.modular.com. The team is constantly monitoring. Chris himself responds to a lot of the stuff there. So definitely a great place to share your questions. Up next, we have Jack Clayton, Mojo Standard Library Engineer, who is going to do a live demo for us of GPU programming with Mojo.
Testing. All right, cool. So yeah, we've gone over time a little bit, so I'm going to rush through it a little. Can I just get a round of hands? Who has done? How many people have done GPU programming with CUDA, like written a CUDA kernel before? Okay, sweet. And has anyone written Mojo here? Cool. All right. So I'll just give a brief explanation of GPU programming as I go. But this is all Mojo code, so it's just a Mandelbrot kernel. You can see there's some parameters up the top here. So alias means it's a parameter. Yeah, sure. How's that? Yeah, so this device context, this is getting a device context for the GPU. So I'm on an NVIDIA machine at the moment. You can see when I do this, I got a A100 that I'm running on here. And then this device buffer, it's in queuing creating a device buffer using the size of this layout. So you can see, as Chris was talking about before, we have this parameter system. So it dynamically, like at compile time, it's actually getting these figures. So you can see that the Mandelbrot grid size is 25 by 60. So it's creating a buffer of that size and then wrapping it in a layout tensor. The layout tensor is a really powerful abstraction based on the Qt library, which NVIDIA has. So it allows you to do a lot of powerful things. And then this is enqueuing the function Mandelbrot to run. So if you look down here, this is a Mandelbrot kernel. So this is like what you would do if you were programming a CUDA kernel. I won't go over like how Mandelbrot works, but basically you can see this is like getting the thread index. So it's getting the index on the Y index and the X index. And then it's doing the Mandelbrot algorithm and just putting it back into the tensor. And then at the end, it just draws the Mandelbrot. So if I run this, you can see the Mandelbrot come back. So yeah, that's running on GPU. And then something that's really cool that you can do, you can actually see the PTX that's being generated. So if I go in here and dump the assembly, and this is running on a remote instance with an NVIDIA GPU. Then that dumps the assembly here. So if I open it up, you can see what the PTX looks like. So you can see the actual instructions that it's generating. And because it's just a Mandelbrot kernel, it's quite simple. So yeah, this is running directly from Mojo, so you can create like a binary and just run things eagerly. But then we can also do things with Python. So if you want to create custom ops that you can run with the Max inference engine, then you can create your own custom ops. So an example is this grayscale. I'll bring this up. So you can see this is the Mojo grayscale kernel, where it's doing the same thing, where it's enqueuing the function to run. So it's enqueuing the GPU kernel to run. The block dims is setting up 16 by 16 grid there. And then the grid dims is using the ceiling to create like a grid across the entire dimension of the image. So what we're going to be doing here, we got this image of two dogs. So that's been loaded in by imread, and that's just a NumPy tensor. And then we're defining the tensor shape. So we have a color tensor and a gray tensor. The input is the color tensor, which is this image here of the two dogs. And then the ops, we have a grayscale, a brightness, and a blur. So these are just wrapper functions to make building the graph a bit simpler. So the data goes to the GPU, it sits on the GPU, runs through one op at a time, and then it gets copied back to the CPU and written to the device. And you can see that code down here, and it'll write out to that one there. So if we go into that folder, And then Magic Run Image Pipeline. So Magic is the CLI tool that allows you to use Mojo and get all the access to GPU programming from Python as well. Just on the first run, it's just compiling the kernels. So the 3 different kernels for the custom ops. And then we can bring up the image. So we got dogs out. And you can see that's just, it's just blurred them, turned them into grayscale and brightened up the image a bit. So you could inject this into an AI pipeline where lots of people will eagerly you can actually put this into the pipeline so that you get a lot of better performance across different batch sizes and things like that. And I'll just quickly show you through the kernels, how they work. So bring this across. So yeah, the grayscale one here. So you can see that it's just looping, like it's got, and it's just getting the has that. Testing. Was that, sorry? Oh, the comma? Oh, yeah, I deleted it. Thank you. Yeah, so that takes an input image with color and then outputs a grayscale image. And then the next 2 kernels, so this brightness one is using like a sort of higher level abstraction using this for each. So for each runs across its CPU and GPU. So like this one up the top here, it's just running on GPU using Q function, but the CPU version can run on CPU or GPU. So I put a challenge in here. If anyone wants to go into the repo, I'll show a link at the end. If you can convert this into using a for each loop, so it runs on CPU and GPU, you get some special Mojo swag, which we'll send out to you. And then the blur kernel down the bottom here. So this is like a little bit more complicated. You can't really use a for each for this because it's taking the 8 surrounding pixels and then getting the average of them so it can blur across the entire image. But yeah, this is just an example of a slightly more complicated kernel. And like Chris said, we'll be open sourcing all the very complicated kernels soon, so you can see how to do super low level performance type things. And there is an example here of top K, and this is using a low level operation using warps, so shuffling down, sharing data between threads on a GPU within the same warp. So for any CUDA engineers, you'll be familiar with that, and yeah, Mojo is fully capable of doing all the low level things that you expect. But the very special thing about Mojo is that this hasn't been announced publicly yet, but all of this that I've shown you actually works on AMD GPUs as well. So this is an AMD instance here, and it does the same thing. So I can run the Mandelbrot. Yeah, and you see it running the Mandelbrot there, and then you can actually see the PTX as well. Not the PTX, sorry, but the assembly. So yeah, you can see the machine instructions for the AMD side. So you can get a comparison about what the difference is between NVIDIA and AMD. And yeah, it's been quite amazing really, because low level stuff like warp shuffles, I didn't expect it to work, but when I just tried to run it on AMD GPUs, it just worked out of the box. And same with all that image pipeline stuff, just worked after the first try. So if you're interested in doing this kind of stuff, I have these 3 links here. So I'll zoom in on that. You have this GPU basics guide, which is just introducing GPU programming. It gives you a kind of rundown of what GPU programming is, but it's still in the early stages. There's only chapter 1 there so far. I'll just show you it. And if you have any problems, we have this forum thread. So if you have any problems with the tutorial, you just post your questions or feedback there. That'd be great. And this is the repo with the eager GPU functions that you can just run from Mojo. So yeah, you can make contributions there. And this custom ops one. So tomorrow the image pipeline will be there with the 2 challenges. If you can get everything running on CPU as well as GPU, you get some special Mojo swag. And that image pipeline will be there tomorrow. So that's essentially it. We have lots of good stuff coming out. Like we realize how to teach the world how to program GPUs with Mojo. So there's lots of stuff coming down. Things similar to like, GPU puzzles and extending the manual and releasing all the open source code so that everyone can get up to speed with programming GPUs with Mojo. And that's it. Is there any questions?
So much, Jack. Any questions?
Oh, thank you, Jack. So I'm Todd. We mentioned NVIDIA and AMD today, and there was kind of a side mention of Apple, but I have an Apple NPU in this, and so have you had any experience?
We haven't started work on Apple Metal yet, but Chris was saying like towards the end of the year in the summer, that we'll be opening it up so people can start working on that themselves, and then they'll be able to contribute and get things running on Apple Metal just like it runs on AMD and NVIDIA. So yeah, that'll be coming at a later date.
Thank you. Any other questions for Jack?
What was the AMD model or the CPU? Sorry, GPU.
Oh yeah, MI3.
MI3 300.
300X. Yeah. So I got it here. Rocking SMO. It doesn't show the model number here, but yeah, it's an MI300X. No worries. Yeah, I keep these red bars and green bars so that I know what instance I'm on. Otherwise, I get confused. At the moment, no. Colab's something that people are looking at, but so yeah, you need access to GPUs at the moment. Yeah, but we want to fix that. So people are looking at Google Colab integration or something similar.
Yeah. So quick question: when you showed the pipeline, it reminded me of 2 things. One was a GStreamer pipeline kind of situation where you build like end-to-end and NVIDIA does support that thing. And the other was basically a graphics pipeline, right? So do you think it's easy enough with where it stands in the Mojo GPU library, you can do some basic graphical stuff as well as something like build an application for like maybe real-time video streaming? Have you guys played around with that?
No, like, so I haven't seen anyone play around with video yet, but it's, definitely like all the tools are there. Like you have the access to all the low-level stuff you do through CUDA. So it's just a matter of someone that's like motivated and wants to get that working. They could do that. So hopefully, as we start releasing more like learning materials, people will go out and build that kind of stuff because we're really excited to see that.
Any other questions for Jack? No? All right, let's give another hand.
Thank you.
Thank you, Jack. That was awesome. So before we kick off the networking portion of the night, I just want to give a chance for anyone who's hiring in the audience, if you want a moment with the mic to share what you're hiring for, so folks can find you when we kick off the mingling portion. If no one's hiring, we're hiring. There are a few QR codes scattered around here. There are also printouts of 4 different roles that we're hiring for up at the front desk. So definitely check those out. And if you had a good time with us tonight, we also have an upcoming modular GPU kernel hackathon at AGI House in Hillsborough. So you can scan this QR code right here to attend. You can also scan that QR code to join our community forum. Drop any questions for the team there. That's the best place to get in touch with